The ampacity of 300 MCM THHN copper conductors with a ground wire in a 2.5-inch conduit is approximately 228 amps according to Table 310.16 of the National Electrical Code. Let's examine the conduit fill. 300 MCM THHN conductors have an approximate diameter of 1.45 inches each, totaling 4.35 inches. A number 2 THHN ground wire has an approximate diameter of 0.425 inches. The total conduit fill becomes 4.775 inches. A 2.5-inch conduit has a nominal interior diameter of 2.465 inches. According to the NEC, the allowable conduit fill is 60%. Therefore, the calculated conduit fill of 4.775 inches exceeds 60% and would not be permitted according to Article 310.16 of the NEC. Pulling 300 MCM feeders with the number 2 ground wire through a 2.5-inch conduit with two 90-degree bends would be extremely difficult, if not impossible. The combination of the large conductor size, high conduit fill, and tight bends would create excessive friction and could damage the conductors or the conduit. To ensure compliance with the NEC and facilitate a successful pull, it is recommended to use a larger conduit size, such as a 3-inch conduit for the feeders and ground wire. A 3-inch conduit would provide ample space for the conductors and reduce the conduit fill to an acceptable level. Now let's consider the factors that affect conduit fill calculations and conductor ampacity. Firstly, conductor size is a primary factor. Larger conductors naturally take up more space within the conduit. Secondly, the number of conductors is important. The more conductors you have, the less free space remains. Thirdly, conduit size plays a key role. Different conduit sizes have different internal diameters, directly impacting available space. Fourthly, conductor insulation type matters. THHN insulation is common, but other types exist, each with potentially different diameters. Fifthly, the National Electrical Code or NEC sets regulations for maximum conduit fill percentages to prevent overheating and ensure safe operation. Now, let's talk more about the NEC. The NEC is a comprehensive set of standards and guidelines for safe electrical installations. It's updated regularly to reflect new technologies and best practices. Several articles within the NEC pertain to conduit fill, conductor ampacity, and related topics. It is important to consult the latest edition of the NEC for the most accurate and up-to-date information. When selecting a conduit size, several factors should be considered. Firstly, the size and number of conductors, as previously discussed, is important. Secondly, directing factors should be considered. The NEC requires ampacity directing when multiple current-carrying conductors are installed in a single conduit. This reduces the allowable ampacity of each conductor to prevent overheating. Thirdly, future expansion possibility should be considered. It's often wise to choose a slightly larger conduit size than initially needed to accommodate future circuit additions. Fourthly, the number and type of bends in the conduit run should be considered. Bends increase friction, making pulling conductors more difficult. Excessive bends may necessitate a larger conduit size or the use of pulling compounds. Fifthly, the length of the conduit run should be considered. Longer runs generally require more pulling force, potentially making a larger conduit size desirable. Now let's further elaborate on ampacity directing. When multiple current-carrying conductors are installed in a single conduit, the heat generated by each conductor can raise the overall temperature within the conduit. This increased temperature reduces the ability of the conductors to dissipate heat, leading to a decrease in their ampacity. The NEC provides tables, such as Table 310.15 CHN, to determine the appropriate directing factors based on the number of current-carrying conductors in the conduit. These directing factors are applied to the conductor's base ampacity rating to determine the adjusted ampacity. For example, if a conduit contains 7 to 9 current-carrying conductors, the ampacity of each conductor must be derated to 70% of its original value. This reduction ensures that the conductors do not overheat and operate within their safe temperature limits. It is crucial to accurately count the number of current-carrying conductors in a conduit to apply the correct dating factors. Grounding conductors and neutral conductors that only carry the unbalanced load from a three-phase system are generally not considered current-carrying conductors for dating purposes. However, neutral conductors that carry a significant amount of harmonic current may need to be counted as current-carrying conductors. The NEC provides specific guidelines for determining when a neutral conductor should be considered a current-carrying conductor for dating purposes. It is also important to note that dating factors can compound when other conditions exist, such as high ambient temperatures. If the ambient temperature around a conduit exceeds 30 degrees Celsius, additional dating factors may need to be applied. These additional dating factors are found in Table 310.16 of the NEC. Failure to properly apply ampacity dating factors can lead to overheating of conductors, insulation damage, and potentially electrical fires. Therefore, it is essential to carefully consider the number of current-carrying conductors, ambient temperature, and other relevant factors when determining the appropriate ampacity for conductors in a conduit. In addition to ampacity dating, the NEC also addresses other factors that can affect conductor ampacity. These include the type of insulation used in the conductor, the temperature rating of the terminations, and the presence of other heat-generating equipment in the vicinity of the conduit. Conductors with higher temperature ratings, such as 90 degrees Celsius rated conductors, can generally carry more current than conductors with lower temperature ratings, such as 60 degrees Celsius rated conductors. However, the ampacity of a conductor is ultimately limited by the lowest temperature rating of any connected terminations, such as breakers or equipment terminals. If a conductor is connected to a termination with a 75 degrees Celsius rating, the ampacity of the conductor must be based on the 75 degrees Celsius ampacity column in the NEC tables, even if the conductor itself has a higher temperature rating. The NEC also requires that conductors be protected from overcurrent by circuit breakers or fuses. The overcurrent protection device must be sized to protect the conductor against overload, but it should not be larger than the conductor's ampacity. This ensures that the conductor will not be subjected to currents that exceed its safe carrying capacity. When selecting overcurrent protection devices, it is important to consider the conductor's ampacity, the type of load being served, and any applicable motor starting requirements. The NEC provides specific rules for sizing overcurrent protection devices for different types of loads, such as lighting circuits, receptacle circuits, and motor circuits. It is also important to ensure that the overcurrent protection devices are properly labeled and readily accessible for maintenance and inspection. Proper conductor sizing, ampacity dating, and overcurrent protection are essential for ensuring the safe and reliable operation of electrical systems. Failure to adhere to these requirements can lead to overheating, insulation damage, equipment failure, and potentially electrical fires. Therefore, it is crucial to consult the NEC and follow best practices when designing and installing electrical systems. In summary, when working with electrical conduits and conductors, remember to prioritize safety and compliance with the National Electrical Code. Accurately calculate conduit fill to prevent overcrowding and potential damage to conductors. Properly direct conductor ampacity when multiple current-carrying conductors are present in the same conduit to avoid overheating. Choose appropriate conduit sizes and conductor types based on the specific application and environmental conditions. Always consult the latest edition of the NEC and seek guidance from qualified electrical professionals when necessary. By following these guidelines, you can ensure the safe and efficient operation of electrical systems.